Hi, so in today's video, I'm going to show you how you can build an image classifier with almost any image. So this tutorial is focused on how can I show you that, or how we can actually do an image classification task with TensorFlow with almost any image. So you can use any dataset of your choice, but I'm going to use a dataset for classifying happy or sad people. And the good thing is we're going to use TensorFlow data pipeline, so you don't need to actually create the data with your own tools. So TensorFlow will do it for you. You just need to have some images of happy and sad people if you want to follow along completely with me. So let me first give you an intuition about how an image classifier works. So in image classification task, we're basically using CNN architectures. So in CNN architecture, you first basically um, feed an image with a certain resolution or certain pixels to the network, and network applies some different kind of layers to it. So first things first, we have convolution layers, and then we have max pooling. We apply the convolution first when the image is fed, and then we follow the image to the next layer, that is the max pooling, and we apply the convolution again, and we apply the max pooling again. Then we actually pass that features extracted to another network, or actually another certain part of this network that are actually that's actually maybe we can say this is an MLP. Um, the second part of a CNN architecture is the MLP architecture. So because basically we are feeding the features extracted from the um, CNN to fully connect the layers, so we can decide which class our image is. Maybe it's happy or it's sad. So let's start the coding. So let's start the coding. So here, first of all, you need to actually have some images. I already downloaded some images from happy and sad people that you can see here. The extension that your images have is not important, and also it doesn't matter how many people are in your image, so you can actually follow along with any image. I have JPG or PNG format. I have everything, almost everything. So I actually downloaded this picture because I was curious. So we need some outliers so we can get a better performance. That's just a certain thing. Okay. So for following along, please have a data directory and some images inside of it. So So first things first, we need to install some dependencies. So let me create Markdown. That is the first part, installing dependencies. So what do we need? First of all, we need TensorFlow, we need OpenCV Python, and we also, or not OpenCV Python, we need CV2. And I guess we need something else too. Let me check it out real quick. Yep, I guess that's all we need. So also, all of the code I'm writing here is available on my GitHub account. I will link it in the description for you so you can actually use it. And I already trained the model. You can just test it out, and you can simply skip the training part and use the ready weights. So first of all, we need to install the dependencies that are, let's do pip install. We need TensorFlow, we need OpenCV Python or CV2, and we need Matplotlib. So once the dependencies are installed, we can head over and remove our dodgy images. So because our images are downloaded from World Wide Web, and internet is not actually removing dodgy or bad images. It's just some images flowing around in the internet. So we need to actually clean up the data set a little bit. So let's actually head over and do it. So removing, and let's say actually getting set up and loading up the data. Okay, so for doing that, we're actually going to import OS, and we're going to need TensorFlow as well. TensorFlow. So then let's actually set up a memory growth for TensorFlow so it doesn't expand and gets all of our GPU memory. So we need our VRAM. And I'm connected to a T4 GPU, so you can follow along with me. I have Google Colab Pro subscription, but I'm actually connected to T4 GPU, so you know you can actually follow along with T4. So let's do GPUs equals tf.config.list physical devices, and we set that as GPU. So it goes and actually looks for GPU devices or CUDA devices. Then we can say for GPU in GPUs, let's actually do tf.config dot experimental, I guess, dot set memory growth. And we pass the GPU and we say true so we can enable that. So let's run this. Okay. Now let's remove the dodgy images. So removing dodgy. So in order to do that, let's actually first import CV2 and image HDR2. So let's import OS and sorry, CV2 and image HDR. Then let's actually define our data directory. So data directory equals data, and let's define our image extensions. So we got PNG, we got JPG, we got BMP, and JPEG. So let's actually do image extensions equals this, create a list for it. JPEG, JPG, can do PNG and also BMP. So then we can iterate over all of these um, images that we have on those two directories and remove any image that is not in that extension. So let's look through it. So let's say for image class in OS the list directory for the data directory. So we're actually iterating in the data directory, that is the data folder, and then we're iterating over each image in this data directory. So then we need to specify each class folder. So let's say for image in OS the list directory, OS the path, the join data directory. So OS the path the join is for joining multiple paths together. So first of all, we need data directory, then we need our image class. So it goes and iterates over each image in each class in the data directory. Then let's say image path equals OS the path the join data directory, and then image class, and then image. So we extract each image path in that. Then let's head over and try reading that path or reading that image with CV2, and then we can check out the extension of that image. And if the extension was not in this list, we're actually going to delete that image. So let's say image equals CV2 time read the image path. So CV2 the time read goes and reads an image from a certain specified path. And then let's say extension equals image hdr dot what, and let's pass the image path, or we can actually, yeah, can set the image path. And then let's say if extension not in image extensions, then if our extension is was not in the certificated extension that we already specified here, we're going to actually say, let's make, let's go and point out um, image not in the extension rest, and we're going to give it the image path, and then let's say except, sorry, except exception as e. Let's print out issue image image path. So let's run this code and see if you get any errors. Sorry, that should be image. Let's do image path. So as we can see, there is no image in this directory that is in another extension of the certificated extensions. So then let's actually load the data. So we're going to dodgy images. So now we can load the data. So let's import numpy and matplotlib. Import numpy as and let's import matplotlib with the pyplot. Then what we can do is to create our TensorFlow image pipeline. So let's say data equals tf dot press dot utils dot image dataset from directory, and then we pass the directory here. Or we can actually say data directory, I guess. That was what we defined. So if we pass this, we actually get 305 files belonging to two classes. So that's what we expect, right? That's how cool is that? You know, that's really cool. So you don't need to actually go through um, all of those image pre-processing and creating batches and then slicing those. So it's doing all the thing here for us. So we can actually create this data. So let's say the type. So this is a prefetch data set. So it goes and fetches our data set too. It fetches them. So we can actually say data.as numpy iterator dot next. So if we do that, we're treating our data as our data variable as actually a data or a ready data set that we can actually extract batches from. So let's actually run this. And if we run this, as you can see, we get image arrays normalized and their corresponding yeah, their corresponding classes in another array here with int32 floats, int32 data types. So these are in float and these are in ints. So that's all we want. So yeah, that's all for data, I guess. But before moving around, let's actually plot some of it. So let's say batch equals data as numpy iterator. Next, so we get a batch here. Then we can create a matplotlib figure for actually getting this batch. So we can actually run this again, and let's say figure and ax equals plt dot subplots. Sorry. N columns equals 4, so we want 4 columns, and our figure size would be 20 by 20. So then let's say for index and image in enumerate batch 0. So when we actually say batch 0, we're actually referring to the 0th element of this batch that this is our the 0th element is array of our images. So because we are trying to actually plotting our images, we're going to have batch 0 because we're referring to the element 0 of our batch. So then we want 4 of them. So then we can say ax index that I'm show image that as type int. So then we can say a title that set text, and then we can say batch 1 because we're now referring to the second element or our actually answers or of our images or classes of our images. So batch 1 for index. So that should do the work, I guess. Yep. The reason these images are so funny and shitty, maybe, is that because I wanted to show you can do it with almost any image. So then let's head over and do data equals data map lambda x and y and y. So we're actually normalizing the pixels, and then we can say data as numpy iterator with next. So we can actually get our data. So as you can see now, our data is normalized and we have our input here. We have our output in another array there. So now we need to split our data. Split the data. So before that, let's add a section called plot. And now if we check out here in the table of contents, as you can see, okay, so now let's head over and split our data into train, validation, and test. So let's say train side. Okay, so let's continue. We're gonna give 70% of our data to training. So let's do int length of our data times 70%. And then we're going to have validation size that is going to be um, data, our length of data, the length of our data times 20%. We're going to give 20% to our validation and 10% to our test size. So let's say test size equals nth length of data times 10%. Then we can hit over and actually get a rate. So let's say train equals data that take train size. So we're taking 70% of our data for train. And we're going to say validation equals data that skip the train and then take the validation size. So it actually goes and skips the 70% of our data that was for training and gets the 20% of those of that 30% that is already there. And we'll say test equals data that skip train plus validation, or we're going to actually say train size here. And here should be train size plus validation size and dot take the test size. Okay, so let's run that and let's print out validation size. So it's a take data set, so we can actually do as numpy iterator dot next. Now, as you can see, it has batches like our full data that we were talking about there. And that's all of it for data, and our data is ready. Everything is ready here. That's all for data. So now let's create another section for building deep learning model. Okay, so for building the deep learning model, we're going to actually use the sequential API of TensorFlow. So let's say model equals, but before doing this, we need to actually import some dependencies. We kind of forgot them, so let's do from TensorFlow dot class models import sequential, and then let's do from TensorFlow dot cross dot layers import conv 2D. It is a convolution layer, and we need a max pooling layer. We need a dense layer, and we need to flatten and dropout. And if you don't know what is dropout is for not having gradient problems. So we're not actually overfitting if we have dropout techniques like L2 regularization or these stuff. So let's use the sequential API. Sequential. So let's define the model as a sequential model, as a sequential instance, and let's do model. Let's add the convolution layer with 16 filters, and so each of those 16 filters is a 3 by 3 pixels filter. So 3 by 3 and then 1, and we're gonna say duration is 0. Our activation is ready, and we need to actually specify the input shape as I told you. So input shape would be 256 by 256 by 3 because our images are in RGB format. Then let's do model. Let's add a max pooling layer, and then let's do model. Let's add another convolution layer. That this one has 32 filters, each one 3 by 3 and 1. And activation of this layer is also going to be ReLU. And the reason I'm using ReLU is because ReLU has um, very good features that let us have more efficient training. And yep, and then let's add another max pooling layer. After that, let's add another convolutional layer. This one is this one's actually has 16 again by 3 by 3 and a 1. And activation is going to be ReLU. So this is the end of the convolution architecture, and then we can head over and actually start the MLP lifetime architecture. So let's flat everything else. Then after flattening it, we can do model. Let's add a dense layer. Let's add a fully connected layer of with 256 neurons because we had 256 here, and also our features extracted are going to have 256 features in a vector, and then we're going to have activation control value, and then let's say model. Let's add another dense layer of 1 neuron. So the reason I'm giving it 1 neuron is because we have a binary classification task, and we need 1 neuron at the output. So in the output, so we get 0 or 1. So then we can have this activation, this layer activation, to be sigmoid, because if you're not familiar with sigmoid is actually a function that gives a value between 0 and 1. So now that's all. That's all of it for the model architecture. Nothing named Latin. Model dot model dot add Latin layer. Sorry for that. And that's all of it for the model architecture. And now let's compile the model. Compile the model. So for compiling the model, we can actually hit over and do model to compile. Let's have the actually uh what is it? Let's have the optimizer as Adam, and let's have the loss function as TF. Let's have actually the binary cross entropy, but it's TF dot losses dot binary cross entropy, and the matrix is accuracy. So let's actually run this. And then let's get a summary of our model architecture. So this is our architecture here. And as you can see, we have a total of 38,000 parameters for training. And now we can actually do the history and train the model. So let's say hist Hold the model, fit only training data, and we have training epochs and our validation data. Data is going to be the value that we specified there. And this should start training. I cut the video and I come back when the training is done. Okay, so it's inside of training, and I actually decided to change this to 15 because we have low data and our data is not qualified really, so let's have more epochs. So I changed it to 15, and as you can see, it's generalizing really good, and our validation loss is still up, but our accuracy is good in epoch 20. So I'm actually loading it done, and when it's done, I'm coming back. Okay, now the training is done and we can head over and see what we got here. As you can see, our accuracy is very good and we have a really small loss. And now we can actually head over and plot the learning curves. So plotting their learning curves. So for plotting the learning curves, we can actually head over and do figure and a. Actually, you can see figure means PLT the figure, and let's say PLT dot plot for hist dot history. For the first one, only the loss, and let's do color, BTO, and label is loss. So now we can do PLT dot plot hist dot history, and actually copy this and do validation loss here, and we can change the color to be orange, and this is going to be validation loss activate. Now let's do figure dot subtitle is going to be loss, and font size, sorry, it's going to be loss here, and font size is 20. Font size is 20, and let's do plt dot legend, and the lock needs upper left, and let's do plt dot shift. As we can see, the loss is actually having some maybe noise, but it's actually generalizing really good in all the epochs. And now let's actually do this for accuracy too. So I can copy this line of code and paste it here, and this should be accuracy, and this should be validation accuracy, and here again accuracy, and here validation accuracy, and this can be accuracy. So let's see the learning curve for the accuracy, and as you can see, these are normal, but we have some noise because of bad data. So now we can head over and check out and test them out. So let's head over and test them out.
So for testing the model, I'm going to actually search for happy people here and download one of these pictures here, maybe this one or maybe this one, and let's download it. So let's upload this in Colab. Let's start this. Let's actually read this with CSV. So CO2 download. Um, this is the path for it. Let's read it. And now let's do PLT that show the image or PLT that time show for the image. And let's do PLT that show source statement. And what is happening? Image data of the type object cannot be converted. What? Let me test out in another image. So I tested out this image and it worked. So now let's actually make a prediction on this. Let's say resize equals cf dot image the resize image and 256 by 256. Then we can do PLT define show resize dot numpy because uh, we're actually creating a tensorflow tensor and dot as type ends. Then we can do PLT data show. So let's see how the resized image look like. So it looks like this. And now let's make a prediction. Let's do YP equal the model predict NP and dimensions and resize 255. So this should make a prediction, and then let's see the Y hat. Sorry, the YP. Let's see the YP. As you can see, this is the prediction it made. And let's actually do if YP was less than or was bigger than 20%. Let's print out um, actually let's say uh, if the confidence was less than this is that less, and else it's the happiness. So this one is the happy class. As you can see, you can change this confidence score. I want 20%, but you can change it as you want. So now, as you can see, our model is performing good, and now we can save the model. So for saving the model, we can import uh, load model class from TensorFlow that does that model. Load model. Let's say model. Save image classifier .h5, and you can actually load the model like this. So you can see more. You can say image classifier equals load model copy model. This here is image classifier h5, and it loads the model and we can test out the model. So that's all for this tutorial. I hope you enjoyed it. If you did, please subscribe and like the button and press the button like below and put down a random comment if you would like. And thanks for watching.